So where I left off last time talking about falling balls, back off one step. Talking about falling balls was this slide, I think. And just to sort of remind you how things stand, I'd already introduced 5 physical quantities back in the talking about skating in the world of inertia and starting and stopping and turning. And so now we're dealing with our first, the first force worth paying good attention to, and that is gravity, also equivalent to the weights of things. And if you drop a ball, so you let go of a ball and leave it to itself, the only thing acting on it, the only force acting on it is its weight. It has all these other things, like it's got mass, it has this concept we call inertia that's playing a role and so on. But the only influence it's experiencing is its weight downward. And that defines it as being a falling object, experiencing only its weight. And its position starts to change with time, its velocity begins to change with time, its acceleration, however, is constant. Its acceleration is caused by forces. I'm just sort of trying to make sure this is as clear in my mind, hopefully therefore clear in your mind, that forces cause accelerations, and because there's only one force acting on the ball, and it's a constant force for all practical purposes here in this room or near in a small venue, it's a constant acceleration that ball's experiencing. It's in the downward direction, because that's the direction of the force, toward the center of the Earth. And to step aside from the details of these various physical quantities and to point out the purpose of the minus sign in this drawing, to make sure that's clear to you. In our real three-dimensional world, the description of all these vector physical quantities, position, velocity, acceleration, force, require that you describe the full direction in which these quantities are happening. This is velocity to the right, velocity toward you, velocity away, sort of away from you and to the left. It's complicated, but in a simplified situation where only one dimension matters, up and down, vertical, you can sort of set aside all the details of having to describe it's heading that way, this way, whatever, and just take advantage of the fact that it's only going along one sort of railroad track. In this case, it's a vertical one. We can just, it's sort of a simplifying notation. That's really all it is. It's just it's a trick of saying, we'll define that as the positive, the world of positive things pointing up. The only other direction anything can point in our little world of one dimension is down. We'll call that negative stuff. So this is positive, this is upward, positive is upward, negative is downward. It's just a simplification and trick. And so in this particular drawing, and often you will see in people playing with motion along one dimension, it's vertical today, but it could have been, for skaters, it could easily be horizontal. Vertical would be a little exciting for a skater. The acceleration, the minus sign is just a shorthand for saying it's a downward acceleration. Is that okay, or questions about that idea? It shouldn't be a big baffling story. The acceleration is 9.8 acceleration units. Which direction? Downward. All right? It's constant, so it stays the same throughout the fall of the ball. What don't stay the same are the velocity and the position. The velocity evolves because acceleration is going on, which is literally a change in velocity. So the velocity accumulates in the downward direction, more and more downward velocity, and the ball picks up 9.8. I wish it were 10 even, and I struggle with trying to 9.8. So it gets about 10 units of downward velocity after 1 second, 20 units after 2 seconds, 30 units after 3 seconds, and so on. And neglecting air resistance, it'll keep going. Yeah? So when I'm measuring downward, am I measuring from the point of origin? Thank you. There's a reference issue for all for the two quantities, position and velocity. Acceleration has an absolute measure. You always know when you're accelerating. You can feel it, and we'll talk about that later. If you're accelerating, your whole body responds to this. Imagine heading forward in a really souped up car, or taking a sharp turn on a roller coaster. You feel it. Okay, so you can feel acceleration. velocity and position both require references. Position's reference is pick a point and live with it. You pick one that's convenient. So for example, 0 was chosen as the point from which I dropped it in this drawing. The other thing that you need is velocity. You need another reference. You need some object that you define as not moving. And your hand, let's say your hand is the one that's not moving. There is an issue of what's known as frames of reference, which I do go into in the book, but never talked about in class. That people who are moving relative to one another, but both moving inertially, that is, they're not accelerating, will have different opinions about velocity and position. They'll agree on acceleration, but they won't agree on velocity and position. For example, this ball, from your perspective, let's define that. So from your perspective, its position in my usual scheme, this is the 0, it's like 1 meter, and it's kind of at this angle. That's its position, right? For me, though, this is my 0. I'm going to call that 0, right there. That ball, first off, its position is not the same as you guys think. It's now, I'll stop for the moment, it's like 15 feet to my left, to your left. So we disagree on the position of the ball. We have different references. And it turns out that physics works just fine with either reference. Choose either reference, but live with it, stick with it. The physics will all work out. We will disagree on certain specific details, but we'll describe the motion the same. So position depends on the reference. You're okay with that idea? Same with velocity. That ball, from your perspective, has velocity 0, right? From my perspective, it's okay. I'm a little teapot. I don't remember. We used to do that. Anyway. I also had exhibitionists in the class who would deliberately have their phone ring. It was a whole mess. Okay. You've all encountered people like that. So back here. Okay, so from my perspective, the ball's moving. It's heading to your right at about 1 meter a second, right? So different frames of reference, and specifically inertial frames of reference. Inertial meaning they're not accelerating. They can look at the world and they'll see different velocities and positions. But if they do all the calculations of a more rigorous calculation-oriented, quantitative-oriented physics, it'll all work out just right in either venue, from either inertial frame of reference. If you're in a frame of reference that's accelerating, like for me, I'm going to start accelerating. And for me, the ball looks like it's accelerating. Wow! It's going faster and faster to your left, according to my accelerating frame of reference. It's not accelerating. And why would this be a problem? There's no force acting on it. The net force on it is exactly 0. And if I'm accelerating, and I can look over and go, wow, it must have a force acting on it. No, the force is acting on me. It's creating a weird frame of reference in which I see things that don't obey the simple laws of physics as I'm describing them to you. If that doesn't make sense, it's okay. Don't worry about it. The issue is, if you're going to look at the world, look at it from a coasting frame of reference, an inertial frame of reference, and everything you see will work out. If somebody's moving relative to you in their own frame of reference, they'll see things differently. You guys can talk about what's going on. Be aware that some of the specific quantities you talk about will be different. Positions will be different. Velocities will be different. Other things will be the same. Accelerations, for example, will be the same because they're caused by real forces. Okay? Other questions? And again, I appreciate the questions. Thanks. Okay, so the velocity accumulates, more and more downward velocity. As this happens, the position changes with time. Here, 0 was the moment you let go, your hand basically position. After 1 second, the ball has descended about 5 meters. After 2 seconds, it's descended about 20 meters. That's much farther. It went much farther in the second second than the first second. And that makes sense, or shouldn't, well, it's right. It's because the ball is going faster and faster. It's covering more distance per second. So if you look for things falling, expect them to travel larger distances toward the end of the fall rather than at the beginning. Okay? What if you, to sort of start heading forward, what if instead of dropping a ball from rest, you throw the ball upward and let go? So the story doesn't start until the ball leaves your hand and you stop pushing on it. While you're pushing on it, it's not a falling object. It's got its weight and you pushing on it. So after it leaves my hand, during that whole trip up and down, when I'm not touching it, it's falling. It's experiencing only one force, its weight downward. And therefore, it's accelerating downward at the same usual rate, the so-called acceleration due to gravity, which here in this room and elsewhere on the surface of the Earth is pretty close to just under 10 meters per second squared, or about 32 feet per second squared. So it's accelerating downward. It's heading upward, but accelerating downward, and that's okay. Remember I talked about this sort of day one-ish, where if, forget the ball, back to the skater story, if I'm heading to your right but accelerating to your left, I slow down, I come momentarily to stop, and then I pick up speed in the direction of the acceleration. So at the start of that story, I was moving to the right but accelerating to the left. So I was slowing down. I was losing my rightward speed, or equivalently accumulating leftward speed, even though I had some right to start with. And this is the same exact story, except now it's vertical. The ball on its way up left my hand, traveling upward fast. And when it becomes a falling object, it doesn't immediately stop moving upward. It's got inertia after all. It's moving upward, but it's accumulating downward velocity. So if you start with a lot of upward velocity and you accumulate a little bit of downward velocity, it just detracts, subtracts perhaps, from the upward. So you lose, it's gradually losing its upward speed and then developing downward speed later in the story. Questions about that idea? Yeah, Dakota. What would the net force be when I'm pushing it up? If it were down, if the net force were downward, which way would the ball accelerate? It would accelerate downward, because net forces cause accelerations, right? Okay. So if it starts at rest, and if its net force is downward, it's going to accelerate downward and begin to accumulate downward speed. It'll go faster and faster downward. Okay. What you're watching it, when I'm holding it, what's it doing? During the moment when I was touching it, what was it? It was accelerating, not now, there. During that period, during slow motion, human animation, right? It started at rest at this height, and it gradually accumulated faster and faster motion upward. Which way was it accelerating? Everybody, show me with your hands, which way was it accelerating? It's an upward acceleration. Is that okay? It's yeah, a few people here are on record with their votes. I told them already, but almost a year ago, end of last year, I went to Moscow and gave a series of lectures. And the people there had already watched some of these class videos. And people during that semester had been putting their feet routinely on this desk during lectures. I'm like totally oblivious. As you can start to see, I'm like, okay? And they're like, what? You know, American students put their feet on the lecture bench? You know, Siberia. Okay. You know, it was pretty fun. You know, several individual people had mentioned this. Like, all right. Okay. So back to the business here. As this is going, it's going faster and faster in the upward direction as I'm throwing it. That means that it was accelerating upward. It went from motionless to upward velocity. That requires an upward acceleration. And forces cause accelerations. Which direction was the net force on the ball during the period when I was throwing it? You all show me with your hands again. Upward. So right now, as we'll see shortly, I am supporting the ball essentially perfectly. What force am I exerting on the ball right now? Tell me the exact amount. Oh, it's upward, right? You can tell me exactly how hard I'm pushing on the ball. What's the amount of the force I'm exerting on it? I'm here. It's hard to do this. It's a named quantity. You can name how hard I'm pushing the weight of the ball. I am pushing upward on the ball with a force that's exactly equal to the ball's weight, but in the upward direction. How do you know that? Because it's not accelerating. So the net force on it is 0. So at this time, I am pushing up just hard enough to balance the ball's downward weight. They sum exactly to 0, and the only way that'll happen is if my push is equal in amount to the weight, but the opposite direction. Is that okay with everyone? Questions about that? All right? To make it accelerate upward, I have to push harder than its weight. I have to push upward more than its weight. And when that happens, it doesn't sum to 0 anymore. It becomes upward. What's it? The net force on the ball becomes upward. So during the toss, I pushed upward on it, not only as hard as its weight, but harder, and made it accelerate upward. Is that okay with everybody? So that's why I said the story doesn't start until it leaves my hand. As it leaves my hand, things are complicated. We'll come to that. I don't instantaneously go from big upward force to 0. I slurp across the whole range of possibilities. And during that time, things are complicated. And we'll sort of come to that with the story of ramps. Have I answered your question, Dakota? Yes. Yes? That's exactly right. Yes. Yeah. Once it leaves my hand, this story is different, but when I'm throwing it, life is complicated. When I let go of it, life is simple. It is experiencing one and only one force. It's weight downward. It's accelerating downward, and that has consequences for its motion. It started with an upward velocity, but that's being sucked out of it, and it's losing that upward velocity. When I talk about it sort of being sucked out, the implication is that velocity is something that is a quantity you can draw out of something. And that's not quite right. But we'll come to the real thing that you are literally sucking out, that's literally being sucked out of it by gravity. And that real thing is a quantity known as momentum. And you've heard tell of momentum your whole life. And the real physics momentum is a quantity of motion that you carry with you when you're moving. And to stop moving, you have to get rid of the stuff. So we'll deal in more detail with it. But the ball leaves my hand with this quantity of motion, namely momentum, upward. And it takes some effort and force and time to get the momentum out of it, which is in part why a way of thinking, a sophisticated way of thinking that we'll come to, of why it takes a little while to stop moving. So if what I'm saying is like, whew, that's okay, we'll come back to it properly in a couple of days. But the idea is that I give it upward momentum by pushing hard for time. I'm pouring momentum into it in the upward direction. When I let go, gravity sucks the momentum back out of it. So in it goes, out it comes. And it ends up actually with some downward momentum when the story's over. Is that okay? So that's a preview. You're now seeing the trailer for episode 5, episode 6, Blue Flame and all that stuff. Okay. Yeah. All right. So when you throw stuff up, the acceleration is purely downward the whole time. On the trip up, the velocity goes from being a large upward to less and less upward to less and less to less to 0, and then it starts to descend as though someone were up there and dropped it at the moment it reached peak height. And the positions evolve correspondingly. Any questions about the upward trip for the ball? All right. What does that leave us with? Oh, well, this question is worth asking, because this one, again, challenges your thinking about this. When you jump upward from a springboard and you dive gracefully in the pool, I'm going to have you jump exactly vertically, which means you're probably going to have a close encounter with the board, but let's imagine somebody whisked it out of the way before you hit it. We're going to let you go straight up and then straight down. Let's look at the moment you're at peak. When you're at the peak, I want to know your velocity and I want to know your acceleration. Is that okay? How many think that your velocity is changing, as in changing with time, but your acceleration is constant? Okay? How many think that your velocity is constant and your acceleration is constant? Okay? How many think that your velocity is constant, but your acceleration is changing? How many think your velocity is changing with time and your acceleration is changing with time? Very light voting. This was the primary before the primary. So what I'm going to do is I'll have you guys discuss it with your immediate vicinity. Make friends with the people around you so you can jibber jabber with them for the problem set later on. But take a minute and let's get an opinion on this. There's an answer here.
So when it leaves your hand and its velocity is upward, is it changing velocity faster when just after it left your hand or right before it?
It's changing the velocity exactly steady the whole time. Its acceleration is constant. The only force acting on it is its weight. So it's the same here as there the whole time. It's lock constant. All right. Hopefully made some progress, made some friends, influenced some people. Let's try this again. You're at the peak. Right there at the peak is your velocity. A is changing with time, but your acceleration is constant. How many think your velocity is constant and your acceleration is constant? Okay. How many think that your velocity is constant, but your acceleration is changing with time? How many think that your velocity is changing with time and your acceleration is changing with time? Okay, we had a substantial change in the voting. Before I reveal, what causes the acceleration? All these choices of acceleration. What's causing the acceleration? Gravity. Is gravity any different when you're at the peak than it was on the way up or the way down? Rock steady. So the force is unchanging. So what's true of your acceleration? It's constant, okay? Second observation is, suppose that you were at the top and your velocity was constant. That's a tear. Yeah. I don't have a good story to tell about. You voted. The main vote was for A. Someone justify why A is the right answer.
If your acceleration is constant, moving downward in gravity, and you're accelerating downward, accelerating is the rate at which your speed is changing, or velocity.
Yeah.
Velocity.
Fraser. Yeah. So Fraser's observation is that you're accelerating, so acceleration is a change in velocity, so your velocity has to be changing with time. The only case in which your velocity won't be changing with time, now I'm embellishing, is when you're not accelerating, when your acceleration equals 0. So the velocity, I was trying to figure out how to show you this. It's tempting to think something's bizarre about the velocity right at the top. The velocity is 0, but only for a moment. On the way up, I'll show you, this is an arrow showing you your velocity. The length of this arrow tells you how much the velocity is. So on the way up, the velocity goes from up and big to less and less and less and less. Is that okay? To 0, and then more and more downward. It goes smoothly through 0. There's nothing special at 0 except that the arrow goes from long up to no length to downward, right? And right there at the center, the velocity is 0, but it's still changing with time. I mean, another variation on this question is your velocity 0 and your acceleration 0? I've had versions of this question where people will vote for an answer in which at the peak, your acceleration is 0 and your velocity is 0. Well, if that were true, you can laugh at other not unknown people. Okay, feel superior to them. It's always, the American way. So you're up here at zero velocity and 0 acceleration. That's bad news, because you go up there, 0, 0, that's your velocity 0, so you're not moving. Your acceleration is 0, so your velocity is not changing. It's still 0. It's still 0. You're stuck. Okay? So that's not happening. I've made way too long a story out of this, but basically, when you jump up and reach the peak and come down, your acceleration is steadily downward the whole time, nothing special about the top. And at the top, your velocity is momentarily 0, but it doesn't stay that way. It's only momentary. You're just swooping through away from, you were upward before, and you're going to be downward in a moment, and you're just on your way through. It's changing away. Any questions about that? All right. I already talked about this one, but I'll remind you, this was last time. You all got it right. That when you throw a ball upward, wherever I put it, once it leaves your hand, you are not pushing up on it anymore. And nothing else is either, neglecting air effects. It's going upward not because something is pushing on it, but because it was moving upward and inertia compels it to continue. Gravity's slowly, it's fighting inertia and therefore gradually sucking away this upward momentum I've described. So it does slow down, but it's going upward not because it's being pushed, but because it used to be heading up and it wants to keep doing what it was doing. Okay? It brings the last part of falling balls. And that is, what if the ball leaves the simple world of up and down motion, vertical motion only, and goes into the world of moving through more complicated, allow it to move left, right, toward you, away from you. And when you do that, the motion is still simple. It turns out that the force of gravity acts only in the vertical direction. And a vertical only force has no effect on horizontal motion. A skater's coasting by. You can load the skater down with bowling balls. I don't know. Pick something heavy and just start handing them to her. And apart from you got to get the bowling ball moving with her, she's going to keep coasting anyway. That added downward weight isn't going to affect her horizontal motion. That's the point. Can you sort of believe that idea? So the motion of a ball that's tossed at an angle simplifies into two halves, two parts. So you throw it at an angle. The up-down part of that. So imagine I'm gonna go over. Here we'll do it. I'll throw it away. I'll throw it away from you. I can't catch worth beans anyway. Okay. So as it was arcing, given that you're sort of looking down the arc, you can't see its motion away from you very easily. You mostly see the vertical part. So you can imagine sort of eliminating the horizontal part of this motion. What's the ball doing? It's going up and down just like it did before when I threw it straight up and down. Nothing changed. It's accelerating straight down. It goes up. It accumulates downward. Now it's called a downward component of velocity. It's accumulating 10 units per second, just like before. So in short, the motion of an object thrown at some cockeyed direction. The vertical part is simply that of a falling object. It rises to a peak and then descends, and its motion is the same as we've just described at length. It goes up to, it loses down, on the way up, it's losing its upward component of velocity 10 units per second. It reaches a peak, its velocity isn't constant there, its component, vertical component of velocity isn't constant, and then it descends faster and faster. You okay with that? Questions about that? At the same time, it's doing the vertical motion. It is simultaneously coasting horizontally. It's coasting because nothing's pushing on it in the horizontal direction. Again, neglecting air. So it covers equal distances horizontally in equal times. Straight line path. It's following Newton's first law. So if you put those two motions together, the up-down motion of a falling object with the coasting motion of a horizontally moving object, you get this arc. It just maps out an arc. It happens to have the mathematical form known as a parabola. I mean, it's not by chance, but it turns out to be that way. But that's what the motion looks like. Questions at this point? Let me show it to you. And I did an online version of the start of this course on Coursera a couple years back. And, can I do that? Yeah. And part of filming that, I went over to the AFC. This is the AFC. And those three guys were shooting from mid-court, and they'd hit the basket every time. Like, I couldn't believe it. So here's this guy over here. If I muck with the lights, we'll never get him back. So here he is on the 836th, sort of almost mid-court shot. He's about to throw it. Ready?
Here is a beautiful three-point shot, right?
Right? Yeah, my voice in the background. Oh, great. I mapped out that shot for you.
To the
Here it
basket.
goes.
And here is that same shot again with all the previous basketball images lingering on the screen. And here is a still photograph of that same shot showing you.
Now, instead of having me from several years ago talking, I can talk live. So that's his shot. You can imagine it's not hard to freeze all the frames of all the basketballs. They're all evenly timed and spaced in time. So they give you the motion of the ball. Oh, come on. This was working a minute ago. Shoot myself in the foot. All right. Oh, my foot hurts. Oh, burned holes right through it. Okay, so I mapped out where the ball was vertically and where the ball was horizontally, every other basketball. So vertically, it's going from this height to 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 this height. It's slowing down. It's getting, the spacing is getting smaller and smaller. It's slowing down, right? And then on the way down, it's speeding up faster and faster and faster. It's doing the motion of a falling ball up and down. Can you follow that idea? At the same time, it is coasting horizontally. Because of where I shot photograph from, and he's a little closer to me than the basket is, the spacing has to evolve. But it's even, the horizontal spacing is nearly perfectly even the whole way across. The ball's coasting steadily toward the basket horizontally. At the same time, it's rising and then falling. All right? That covers all these falling balls. You know, a zillion sports have this going on in them. And you get used to knowing where the ball is going to go. I mean, think of how amazing it is that people who play sports better than I do, can anticipate where the ball is going to be in this whole flying arc. You know, they know it's going to be here, not here. After it's gone a crazy distance, you're essentially doing that calculation automatically, knowing the rise and fall and the steady motion downstream. You do it by experience and intuition, but this is the physics behind that motion. Okay? Any other questions about falling balls? All right. Let me get rid of this guy, and I'll go on to the next topic, which is ramps. All right. So, can a ball, it seems to have nothing to do with ramps, but it will. Can a ball ever push downward on a horizontal table with a force that is greater than the ball's weight? So for example, this bowling ball, right now, it's pushing down the table. If your hand were there, you know how hard it's pushing down. Can it ever push down harder than that? And if I don't stipulate that something is forbidden, it's allowed. Okay? That comes up from time to time. You know, anyway. You okay with the question? How many think that yes, it can push harder than its own weight on the table? How many think no, it can't push harder than its own weight? It's actually about 50-50. Given the time, let me say, can someone think of a situation where the ball might push harder than its own weight on the table? Kate? Okay, this is, so her observation, if I'm pushing on the ball will push on the table extra hard. That is true. And so now I'll stipulate one more thing. One new thing. You're not allowed to touch it. No one's allowed to touch it. It's all by itself. Okay? Will that change people's votes? How many think that yes, it can push harder than its own weight on the table? How many think no, it cannot push harder than its own weight? Ooh, big change. Okay, so basically no one, now people are saying no, it cannot push harder than its own weight. Can someone think of a scenario where? Like drop it. Put your hand mentally under the ball. Did it push harder on your hand than its own weight? I'll ask the question again. How many think that it can push harder than its own weight? Yes. How many think no? Ooh, big change. So if you're allowing it to move, yeah, it can push as hard as it likes. And this is like the whole story of impacts. When things hit, they exert impact forces, just to name them. It's not like great, don't write impact, well, impact force, now I know something. No, it's just a name. But during the process of stopping, you think what the ball was doing. The ball was heading downward, helped by gravity in this case, but it doesn't have to be. I can get an impact force. The ball pushed on a wall plenty hard when it hit. I could have used a harder ball and dented the wall, but I didn't. So it's not about gravity. It's about when an object is moving and it encounters a surface, the surface goes like, wait a second, I'm here. People walking here, like, don't smash me. And so it pushes out. The ball pushes in, saying, I'm going there. Wall says, no, okay? They push very hard on each other. And those forces during that impact have lots of effects. I mean, they hurt if you're one of the objects. And the point of the wall's push on this ball is to stop the ball from moving to the right and make it move to the left. Where'd the ball go? During that impact, the wall is pushing much harder than the ball's weight or anything related to weight to cause it to accelerate to a stop and possibly even to rebound, which is we'll come to down the road. But anyway, during impacts you can have enormous forces. What this does bring up is a new kind of force. We've got gravity around, but what happens when objects touch each other? And it turns out they exert forces on each other because they do try to keep from occupying the same space at the same time. And those forces in which they push apart are known as support forces. I call them support forces. You may have encountered them with other names. Normal forces and contact forces. It's the same thing. So right now the fact that the ball is not accelerating means it's being pushed, not just by gravity, but by something else. And that something else is the table. And the table's pushing up with a force that exactly cancels the ball's weight. So we know how big the force of the table on the ball is. It's a force equal in amount to the ball's weight, but upward. During an impact, the table can push harder than that, because not only does it have to support the ball's weight, but it has to cause the ball to accelerate upward, to stop it from heading downward. And that's when it pushes extra hard. And any questions? I mean, I'm meandering through the content of what I will talk about. So some of these things we'll come right back to. Observations about ramps. It's there, you know, when you're moving stuff around, you don't get to use ramps much in moving in and out of dorms, but okay. When you're moving really heavy stuff, lifting it straight up to your 8th floor apartment is difficult. Why? Because at the very least you have to support its weight, and that could be a challenge already. And even worse, you have to cause it to accelerate upward, so you have to push harder than its weight to make it accelerate upward. So life is difficult. What's the alternative? Go up a ramp. So when you make your $8 billion and you decide to build a pyramid to yourself, you can use ramps to do this. The heavy blocks, no problem. Somehow the ramp allows you to do things you couldn't otherwise do. It's providing part of that upward force somehow necessary to lift things up. You also just, what else with this? The push that's required to get something to go up a ramp, and we're neglecting friction for the moment. There are various ways of sort of burying friction, one of them being wheels. So we're going to not worry about friction, but if you're pushing something up a ramp, you know from great experience, a grocery cart trying to go up a ramp, you know that the steeper that ramp is, the harder it is to get the thing to go up the ramp. The push that's required on a grocery cart gets worse with steepness. And for people with disabilities and handicap ramps, there's a limit to how steep the ramps can be for that very reason, because beyond a certain steepness, they're not helpful. You can't, the push required to get up it becomes too much. All right, so what else about the slope of the ramp? The gentler the slope of a ramp is, the less hard you have to push on something to keep it moving. For example, at constant velocity up that ramp. But there's a cost to this. If you make the ramp shallower and shallower, yeah, it's easier to push things up it, but you don't get much rise in height. The ramp has to get longer and longer to lift something to your 8th floor apartment. So there's some trade-off going on here, and because we flesh out that trade-off in terms of physics, and we will. All right, so the questions that I'll go through in dealing with ramps are these, and the first one is simply, why doesn't a wagon fall through a sidewalk? And this brings us right back to something I was just talking about, and that is these so-called support forces, or normal forces, or contact forces. If you've got a sidewalk, and so this is my ramp that I'm going to play with here, and obviously I can make it steeper and steeper. It can go all the way from horizontal, which is the shallowest possible ramp, to vertical, which is the steepest possible ramp, and we'll see that the whole range is interesting. But let's start with we'll start with the horizontal. And there's the wagon. There's you. Enjoy your ride in the wagon. This is sort of the boring part of being in a wagon. You're on a horizontal surface, and the net force on you is 0, and you started at a rest, so you're going to stay there for the rest of class. So why doesn't the wagon fall through the sidewalk? And the answer is that the sidewalk resists this tendency for the wagon to go through it. They don't want to occupy the same space at the same time, so the sidewalk pushes up on the wagon with a force exactly equal to the wagon's weight in the upward direction. We're okay with that? Net force 0, I mean, you can do the whole story. It's not accelerating, so the net force must be 0. The net force is 0, so that the two forces acting on it must sum to 0. What are the two forces? The weight down, the support force up from the sidewalk. Those two must sum to 0, so we know what the up push was. All right. Good. So that begs the question, why does the sidewalk push just that hard? Why doesn't it push a little harder? Why doesn't it push a little less? How does it know to push? I mean, it's not the wagon, it's not gravity. Why is it pushing with a force that exactly cancels the wagon's weight? It didn't have to, there's no law. I mean, at least no legislative law. So the answer is that actually there was a negotiation that occurred when I landed. So here, right now the sidewalk doesn't even know the wagon exists. It's wearing sunglasses. eclipse glasses. Can't see. I can't see. Okay, when I put it down, now the sidewalk knows, and the sidewalk begins to push up with a force that exactly balances, cancels the wagon's weight. But during the landing process, there was actually a negotiation that occurred between the two objects, sidewalk and wagon. And it happened very fast, and you didn't notice it happened, and most physics courses sort of just ignore it. But it's real. Let me show you landing the wagon not on the sidewalk, but on a spring scale, which will tell us how hard it's pushing. This thing like you know, back when groceries used to have spring scales like that. When I land it on the sidewalk, that's real. Did you see the needle go back and forth? Now you know what to look for. Watch the needle. The needle is telling you how hard it is pushing up on the wagon. And the needle went back and forth about where it settled. It settled here at 60 newtons. It is currently, that is cockeyed. What happened here? No. Don't tip the canoe, or the plane. Hey, look, there's a volcano erupting over there. Everyone in the plane goes to the left side of the plane. Wow, the plane tips over. You know, I would say it's Friday, but it's only Wednesday. So that negotiation was real. What was happening during the negotiation process, where the sidewalk, now the grocery store scale, was trying to figure out how hard should I push up on this thing? Well, let me try with only a little push. So if it only pushes gently up on the wagon, the net force in the wagon is downward because it's not being supported properly. So it accelerates downward and it begins to descend faster and faster. And the grocery store scale discovers the wagon is pushing down on it, is descending into it. So it says, whoa, I underestimated. I'll push harder because otherwise it's going to have wagon in its guts. So it pushes harder and harder. Eventually, it pushes just hard enough to support the wagon as it's being squished downward. The harder you squish virtually anything you ever encounter downward, the harder it pushes up. This is a characteristic of springs and elastic stuff, a trampoline. If you push down a little, it pushes up a little. You push down, if you descend, make a dent deep, it pushes up hard. So as the scale or the sidewalk are being pushed downward farther and farther by the descending wagon, they push up, the sidewalk or scale push upward harder. There comes a moment when the sidewalk is exactly supporting the wagon. It's a special moment, situation known as equilibrium. The net force in the wagon now is zero. It is in equilibrium or at equilibrium. But it does not stop there because when net force is zero, does that mean you're not moving? It means you're coasting. It means you were doing what you're doing. And in this case, the wagon was heading downward. So the wagon reaches equilibrium, perfectly supported, but it was moving downward when it reaches that equilibrium, so it overshoots. It continues downward and overdents the sidewalk. Once the sidewalk's overdented, it pushes extra hard up on the wagon. The wagon accelerates upward, and pretty soon the wagon begins to rise, and much to the relief of the sidewalk. It reaches equilibrium again, but overshoots again. This whole bouncing motion, up and down, about equilibrium, is this attempt on the part of the two main actors, the sidewalk and the wagon, to find equilibrium and settle there. And they overshoot back and forth for a while until they settle. And we'll come back to this bouncing process because it's everywhere in the world around you on Friday.